Have you ever wondered how a single simple shape can describe something like the arc of a thrown ball, or the curve of a satellite dish, or even a sound wave? Well, today we're going to dive into the amazing toolkit of function transformations.
Okay, think about it like this. You've got one single footprint stamp. Just by moving it, turning it around, maybe pressing a little harder or softer, you can create a whole unique path. That's exactly what we do in mathematics with graphs. We start with one basic parent graph, and we learn how to move it, flip it, and stretch it into an infinite number of new possibilities. So, here's our game plan. We're going to cover how to shift graphs, how to reflect them, and how to stretch and squeeze them. And then we'll put it all together to see how we can build brand new, complex shapes from these simple moves.
All right, let's jump right in with the most straightforward move of all, shifting. This is literally just about picking up our graph and moving it somewhere else without changing its actual shape. First up are vertical shifts. And the rule here, it's super simple. When you add or subtract a number on the outside of the main function, you're hitting the y values directly. Add a positive number, the whole thing goes up. Add a negative number, it goes down. It's exactly what you'd think it would do.
And this visual shows it perfectly. See that original blue function? When we just add 1 to the whole thing, every single point on that blue curve just scoots up by 1 unit to create that new orange curve. Nice and intuitive.
Okay, so now let's talk about horizontal shifts. This is what happens when we make a change inside the function's parentheses. And, this is where things get a little weird, because the effect is the total opposite of what your gut tells you.
You heard that right. You see x plus 1 inside the function, and you think, move right, but nope. It actually shifts the graph to the left. And if you see x minus 3, that moves it to the right. So why on earth does that happen?
Well, it's all about the input. To get the exact same y value that the original function had at x equals 0, our new function now needs an x value of -1 to make the inside of the parentheses equal 0 again. So you have to use a smaller x, which ends up pulling the whole graph to the left.
Okay, next tool in our kit, reflections. This is pretty much what it sounds like. We're going to create a mirror image of our function across an axis, kind of like looking at a mountain's reflection in a perfectly still lake.
And yep, just like with shifts, we've got two types. If you stick a negative sign outside the function, you negate all the outputs, and that flips the graph vertically, right over the x-axis. But if you put that negative inside the function with the x, you're negating all the inputs, and that flips it horizontally over the y-axis.
And this slide just shows it so clearly. A negative on the outside flips it down. A negative on the inside flips it sideways. See that pattern? It all comes back to that same inside versus outside idea.
All right, now for the really fun part. Let's start warping our graph's dimensions by stretching it and squishing it. This is how we can change the steepness of a curve or the intensity of a wave.
Vertical stretching is nice and intuitive, just like the vertical shifts. When you multiply the entire function on the outside by some number, let's call it a, you're just changing its height. If a is bigger than 1, you stretch it taller. If a is a fraction between 0 and 1, you compress it, you squash it shorter.
What's really cool here is how you can see the y values changing directly. That blue curve is literally twice as tall at every single point as the original black one. The orange curve, exactly half as tall. But notice, the horizontal position, the x values, they don't change at all. And you can probably guess what's coming next. When we multiply inside the function, things get counterintuitive all over again. Multiplying the x by a constant is going to stretch or compress the graph horizontally, but it's going to do it in the opposite way you'd probably expect. So here's the bottom line. Multiplying the input by 2 doesn't make the graph twice as wide. No way. It actually makes it twice as narrow. It squeezes it horizontally. And on the flip side, multiplying by 1/2 stretches it out, making it wider. It's that same backward logic we saw with the horizontal shifts. Okay, if you remember one thing from all this, let it be this. This is the big rule, the master key. Anything you do outside the function's parentheses affects the graph vertically, up and down. And it does exactly what you'd think. But any changes you make inside the parentheses, to the x itself, that affects the graph horizontally, left and right, and it does the opposite of what you'd expect. This one rule governs everything.
So we have our tools, right? We can shift, we can reflect, we can stretch. Now let's put it all together and see how we can combine them to build some really interesting and complex functions.
Now listen up, because this is incredibly important. When you start mixing and matching these transformations, the order you do them in matters a lot. If you have a shift and a reflection, doing them in the wrong order will give you a completely wrong graph. You need a system.
And here's a reliable order that works every single time. Think of it like PEMDAS, but for graphs. First, always handle any horizontal shifts, the stuff happening inside the parentheses. Second, apply any of your stretching, compressing, or reflecting. And last, you can finish up by applying any vertical shifts. Follow those steps and you'll nail it.
So why does all this matter? Well, because with this simple toolkit, you can take a basic function like a parabola, and you can transform it to perfectly model the path of a basketball, or the shape of a bridge, or even the signal from a radio telescope. This is the language that we use to describe the world around us.
So the next time you see a repeating wave, or a symmetrical arch, or a decaying curve, just ask yourself, what simple parent function is that? And what transformations did we have to apply to get it there? The world is just full of functions out there, waiting to be described. Thanks for watching.